Let us talk about this problem. We are supposed to implement k stacks inside a single array. So we have a single space and we are supposed to implement k stacks inside it. So this might be requirement situations where you want multiple data structures to be implemented in the contiguous memory block, so that you might want to have cache friendliness, locality of reference, right? So we need to design a data structure k stacks that will use an array of given capacity. Capacity is provided as a parameter and k is the number of stacks that you want to implement inside the array. And you would want to have a constructor and you would like to have functions like push, which will take stack number as an argument. Stack number is going to be any value from 0 to k minus 1. You can rather call it stack index, right? And a value x to be inserted in this particular stack number. Now a pop function should take an item out from given stack number and is empty function, and you are supposed to implement these three functions in big O of one time complexity. Now as we have already discussed a similar problem when we talked about implementing two stacks in an array, and we talked about a naive solution. A similar naive solution can be done here, that you have a whole array, right? And suppose you want to implement three stacks inside it. So what you do, you divide the space into three equal parts, right? You use this part for the first array, first stack, second stack, and third stack. The problem with this is, if this stack becomes full, right? And if you want to insert more items in this stack, you would not be able to insert items even if there are spaces available in the remaining two stacks, right? So we are supposed to implement k stacks in a way so that we don't waste any space. And to give you a hint, you can use auxiliary arrays. See, the actual stacks might not be of integer types. It might be of a student type or class teacher type or subject type, any large object, any business large object. But the extra arrays that you are going to use, that will be of integer type. So the idea and or hint for this problem is, you will use an array of the given type, which is integer here for simplicity, and you will use some extra integer arrays to make sure that you build k stacks inside the array without wasting any single slot of this array, right? So if there is any single slot available in this array, your item should go to that slot. So that's the problem. Now please pause this video and try to think of a solution that implements these operations efficiently and does not waste space in this array, right? This array might be an array of large objects, but you are allowed to use extra arrays, right? You are allowed to use extra arrays. And to give you more hint, we are going to use two extra arrays, right? And one extra variable, and with the help of those things, we will be able to implement k stacks. And one extra array is going to be size k, and one extra array is going to be size n. So I have given you enough hints. Before looking at the solution, please try implementing this solution yourself. Let's now take a look at the implementation. We have a structure k stacks. We are using a structure in C++ so that we don't have to write public, right? A structure has everything public by default. Then we have these three arrays, ARR, top, and next. Then we initialize then we have these members, k, number of stacks, free top, top of the stack, capacity. Now we have a constructor. Inside this constructor, we are initializing things. So if n is 5 and k is 2, we are going to create an ARR array of size 5. That's what we have done here. Then we are going to create a top array of size k. That's what we've done here. Then we initialize this top array as -1, right? And then we have next array, and next array from 0 to capacity -2 indexes, we have values as I plus 1, right? And last index has value -1. So that's what we have done in this loop. Free top is initialized as 0, top of the free stack. Everything is in the free stack as of now. Next of 0 is 1, then 2, then 3, then 4. There is nothing below this. So we have next of this 4 as -1. Let's now talk about the push operation. What we do in the push operation, we take a free slot, right? And here, to keep the implementation simple, I'm not handled overflows, right? You can handle overflows. If free top becomes -1, then your free stack is empty, right? So you can handle overflow that way. So we first get a free slot, right? And here, when you are getting a free slot, what all you need to do is, you need to make sure that your free list is maintained, your next values are maintained in the free stack, right? And your current stack next values are also maintained. So what we do, we first take a free item and we assign the index I, right? We know that our element is going to be at this index, so we assign ARR I at the x. So suppose we want to insert push 100, stack number is 1, which means second stack. and we want to insert the value 100. So what we do here is we first take the free top is 0, we go to that index and put the value 100. The old value of free top should become the new top of the stack because you've taken the slot with this index 0. But you also need old value of top. Right now it's -1, but you don't know if there were more items before it, right? So we use the old value of top. If you take a closer look, we assign the top old value to next I, right? So whatever index where we have inserted the item, we have inserted the item at index 0. 0's next is going to be the old value of top. Old value of top is copied here, right? So -1 means there is nothing below 100 in this stack or nothing next to 100 in this stack. But we need to ensure that we copy the old value, right? And we also need to update the free top, right? The free top is going to be next of I. So we first ensure that we update the free top, because if I do this operation first, I'll lose track of next I, right? So first I update the next top. This order is really important, right? You can do array I here at the top, but this order of operation is important. First we update the free top, right? We get the next of next item in the free list. Then we update the next of I as top of Sn, right? Because now this slot, I slot is belonging to this stack Sn, right? So we update the next of I to top of this stack, the previous top of this stack. And then we update the top of this stack as I, right? This is how we do a push operation. Let's do one more example. So I want to stack, insert 200 and stack at index 1. So I get a free top is now 1. I go to that index and I write 200, right? Then what I do is I update free top. And free top is now going to be the previous value of top. Previous value of top is 0. Now it becomes 0. And what is the value of top now? Top value is going to be free top value, previous value of free top, which is going to be 1. So these updates we make, and we also update the free top as next item in the top free list, right? We first get the next item and assign it to the free top. So free top now becomes 2. So this is how our push operation works. Let's now see the pop operation. In the pop operation, what we need to do is we need to remove the top item of the stack and we need to assign the slot to the free stack, right? So what we do, we first get the index of the top item because that index is now going to be part of our free stack. So we get the index, right? And then we move the top of the current stack to its next item, right? Top of Sn, and if I use this index, next I would get the next of current item in the stack, right? And the index of the previous top, now we what we do is we make the current free top as next of it, right? Because this item is now going to be on the top of the last free slot, right? So so what we do, we make next of I as free top, right? So if you take a look at diagrammatically what happens here, we removed this one from the stack, right? This 200 from the stack. So what we do is we use this slot 1 as a free slot now, right? So to make this free slot, this is going to be a free top as well. You can notice that it's free top. But before we make it free top, we need to make the current free top 2 as next of it, right? Because the current free top is going to be the next free item in the free stack. So that's what we do here, right? We make the next of I as free top. And then we make free top as I. And at the end, we return array I, the item that we removed from the stack. So this is how pop operation works. If you take a closer look at all these operations, the push and pop, these two operations are particularly big O of 1 operations. That's what we expect, right? And we never waste any space in the array. If there's space, we are able to push that item because we are maintaining free stacks separately by using these auxiliary arrays, next, and top, and a free top variable, right? With the help of these things, we are able to best utilize the space and we are able to ensure the time complexities as big O of 1 for push and pop. Let's quickly see our last operation, which was is empty. Given a stack number, we need to find out whether it is empty or not. So this function is really simple. We just need to check if top of Sn is -1 or not. If it is -1, then the current stack, the given stack is empty. Otherwise, it's not. So it's again a simple big O of 1 operation.